All right, so we're going to start looking at trigonometry. Okay, trig is going to go up through chapter 8. And before we start, I just kind of want to take a look at that word, okay, trigonometry, and just kind of break it down and see if we can figure out what it means. So trigonometry, really, you've got kind of the prefix there, tri, and metry. And we could even extend that to saying trigon. But let's kind of look at those three parts separate. What does tri mean? Three, yeah. And how about something that ends in the word gon? Yeah, like a polygon, so or an octagon or hexagon. So it has to do with a two-dimensional figure with a certain number of sides. So trigon is a three-sided, two-dimensional figure. It's not the word we normally use. We usually use triangle. But every shape has a name that ends in gon. We use it for shapes that have more than 5 sides generally, like pentagon, octagon, decagon, things like that. But even a 4-sided shape, there is a name that ends in gon. Anybody know that? Name for a 4-sided shape? How about, does anyone know the regular name for a 4-sided shape we use more often? That's a specific one. Quadrilateral. So that's the 4-sided, the name of a 4-sided shape people normally use. But you can also call it a tetragon. Okay? And if you've played Tetris, you see all the blocks. Each shape in Tetris has 4 blocks to it. That's why it uses the prefix tetra, okay, for meaning 4. Yeah. Yeah, all the shapes in Tetris have four blocks because it's tetra means 4. And then metry. Okay, you see that prefix at least with a couple different subjects like trigonometry, geometry. Does anybody know what metry means? My tree? Not quite. Metry means measurement. All right, so trigonometry really has to do with the measurement of triangles. Okay, and we can use measuring triangles to do all kinds of things. We can measure, like calculate, let's say you had the ground and you had a building, okay, and you're standing right there. If you know how far away you are from the building, which that's usually easy to measure as long as you can just take a tape measure and measure how far away you are, and you could measure the angle to the top of the building. That's a little harder to do, but if you have like a transit or something like that, you can measure the angle to the building. You can find the height of the building, okay, as long as you know the angle to the roof and how far away you're standing. Okay, there is another way to do it too. If you don't know how far away you are from the building, you can do it with just measuring the angle, but you have to measure 2 angles. Okay, it's kind of like you got to stand in one spot, measure the angle, and then back up and stand in another spot and measure another angle. The first way we'll talk about when we get to right triangle trig, because when you do it the first way, you end up making a triangle. Right there, that's a 90-degree angle. The second way when you do it, you end up making a triangle more like this. Okay, so we still have a triangle, but there's no right angle in it. So triangles without right angles are a little harder to figure things out, but we can still do it. All right, so we'll study a lot of things with right triangles, but we'll also study triangles that don't have right angles. All right, and some applications like finding the height of a building or the width of a river, or all kinds of things we can do. All right, so we'll just start out with kind of the basics about what angles are, how we draw them, how we measure them, and then we'll get to how we can convert between degrees and the other unit we can measure. All right, so there's the definition of an angle, basically from geometry. Okay, so an angle is made up of 2 rays with a common starting point called the vertex. Okay, and I'm going to draw a picture in a second. Now, that's the definition of an angle when you just sketch it by itself. In the red and the blue triangle, those are still considered angles, okay, inside these triangles. But the sides of a triangle are not rays, okay, they're line segments. So even though a triangle has 3 line segments, and the angles are between the line segments, we still consider those angles. But if you're going to sketch an angle just all by itself, usually you draw it as two rays. And when you sketch both rays, one ray is called the initial side, the other ray is called the terminal side. And the way you can figure out which side is the initial and which side is the terminal is you start at one side and you rotate counterclockwise, okay, between the rays. Okay? So technically here there's two angles. There's the angle that's inside the rays, okay, the one I drew in red, but then there's an angle on the outside as well. Most of the time when we're talking about angles, we deal with the angle that's inside the rays, okay? Not the one on the outside. Okay, so in this example, that's my initial side, the one that's almost horizontal, and the terminal side is the one that's coming up at an angle. Okay, if I drew something like this, the rotation again, you start at one side, you rotate counterclockwise to the other. This would be the initial, and this would be the terminal. Okay, any questions on that? So you might see a problem in the homework either tonight or tomorrow that says they want you to draw an angle where the terminal side goes through the point 0.5 or 0.7 or something like that. Okay? If they give you a problem like that, what they mean is to do something like this. Okay, there's our graph paper. And they say, if they said, for example, the terminal side goes through the point 0.5. There's the point 0.5. They just want you to draw the terminal side right there. Now, they didn't tell me where to put the initial side, but I'm going to tell you in a second where you always put it, if they don't tell you. Okay. Does anybody have a guess where you put the initial side if they don't tell you where to put it? Yeah. Yeah, it's on the positive part of the x-axis. Okay, so if they don't tell you where to put it, that's where you put the initial side. I'm going to tell you that and write it out in a second. Okay. And if you do draw it just the way I explained to you with the initial side on the positive x-axis, there's a special name for that. And we'll get to that in a second. All right, so when we're talking about an angle or we need a way to represent it, a lot of times in trig they use a Greek letter. Just like in algebra, a lot of times they use x for the variable, but technically you can use anything you want. Same thing here. A lot of times these are the letters they use to represent angles, especially the first three, actually the first four. But technically you can use any letter you want. You could use x to represent an angle. Okay, but this is generally what they do. So let's just go through them. You're not going to see all of them today, but just make sure we know the names of them. How about this first one? Yep, that's alpha. How about the second one? Yep, that's beta. First two letters in the Greek alphabet. How about that one? Kind of looks like a Y, sort of. Anybody know that one? That one's gamma. Okay, and these are also all lowercase. Okay, just like in the English alphabet, there's a capital alpha, capital beta, and capital gamma. Which one? Nope, that's not omega. The last one is actually going to be omega, one that looks kind of like a W, but the sides are curved and it kind of loops on itself in the middle. That's omega. The one with the circle in it is theta. Okay, now if you've seen this Greek letter, that is omega as well, but that's the capital omega. Okay, what I've drawn is lowercase omega. Okay, that is used quite a bit too. Not as much in this class, but if you do anything with electricity, you might see that symbol. Yep, for resistance.
First period teacher, please.
Okay, so as I mentioned earlier, if they don't tell you where to put the initial side, there's usually a way we always draw the angle, kind of the standard way, and it's called standard position. For an angle to be in standard position, two things have to happen. One, the initial side has to be on the positive x-axis, and two, the vertex has to be at the origin. Okay? As long as both those things happen, that's an angle in standard position. Okay? So if I took this angle and did that, is that standard position? No. What's wrong with that? Yeah, the vertex isn't at the origin. The initial side is still on the positive x-axis, okay? But the vertex isn't at the origin. Okay? What if I did something like that? Is that standard position?
No, because the initial side isn't on the x-axis.
Right. The initial side isn't on the x-axis. The terminal side is on the y-axis, but we don't care about the terminal side. The definition of standard position doesn't have the word terminal in it at all. Okay. So again, standard position, vertex at the origin, initial side on the positive x-axis. Any questions on that? All right. So one way that we can measure an angle is in degrees. Okay, and this is going to lead us into the other way we can measure an angle and how we convert between the two. Okay, if you did one complete rotation, okay, on a circle, how many degrees would that be? Yeah, that's 360. Now, there's two directions you can measure angles in. There's clockwise and counterclockwise. Okay, so let me show you the difference. I've got a little program. I can draw an angle that's 360, and I bet you can guess the difference between what happens if you go one way versus the other. All right, let's. All right, so this is a program that lets me draw angles. I can only move the terminal side, so all angles that I draw are in standard position. Okay, and there's an angle that's 124 degrees, and I can keep going until I make one complete counterclockwise revolution. And it's kind of hard to stop right on it, but it's 360 degrees. Now, anybody have a guess what would happen if I go the other way? Yeah, you do. You get negative angles. All right. So the only difference between a positive and a negative angle is the direction. Okay. Okay. What if you did a half counterclockwise revolution? That would be 180. And how about if you did a quarter? 90. Okay. And that's important to know because a lot of times when we draw our angles, we're always going to draw an x and a y axis, and we label the 0, 90, 180, and 270. And again, 0 is the same as 360. And there's a name for those kinds of angles. So we'll talk about that in a second too. Okay, so angles that are measured counterclockwise, okay, are positive. Angles that are measured clockwise are negative. All right, so I'm going to put that chart back up, and I'm going to draw a 270-degree angle. And I want to see if you can tell me what it would be the same as if I went the other way to get to it. Okay, I'm going to go counterclockwise. Okay, so here's a 270-degree angle going counterclockwise. It would be the same as a what? Not a 90. 90 would end up here. Negative 90. Okay? So negative 90 and 270 are angles that have the same initial side and the same terminal side. There's no difference where those two sides landed. Anyone have a guess? What could you add to negative 90 that would turn it into 270? Yeah, you can add 360. And in fact, you can add 360 more than once. If I add 360 again, all that that's going to do is give me an extra revolution. So 630 is another angle that has the same initial and terminal sides as 270 and negative 90. In fact, there's infinitely many angles that I could draw that have the same initial and terminal side. I just have to keep adding more and more revolutions, okay? Either in the positive direction or the negative direction. And all you have to do to keep getting these angles that I'm pausing at is add or subtract 360 as many times as you want. Right? And that'll keep giving you the same initial and terminal sides. Does anybody have a guess, out of all the angles that I stopped at, which one is the one that's the easiest to use? Yeah? Okay, negative 90. That one's not too bad. Or the other one you might say is 270. In general, a lot of times we pick the angle that's between 0 and 360. Okay, we don't like to work with angles that are like negative 800 something. It's kind of hard to visualize. So we would add 360 a couple times to it. Okay? That's a little easier, and that's even easier. We will deal with negative angles a little bit when we get to inverse trig. Okay, not this week, but negative angles come up a lot when we do inverse trig. But as far as like measuring angles practically, like in a triangle, you'd never have negative angles. So a lot of times they deal with positives. And even then, there's a limit to how big an angle can be in a triangle if you know a little bit about triangles. Right? But we'll get to that later on. I already mentioned this idea to you that angles can be larger than 360, and that just means you have more than one revolution. And I should say they could also be smaller than negative 360, which means you have more than one revolution in the clockwise direction. Generally, I'm not going to have you sketch angles that are more than 360 on paper, but if I did, like if I said to you, sketch a 450-degree angle, would look just like this. That's your initial. That's your terminal. But 450 degrees means you've gone around like that. Okay, you made one revolution that's 360, and then you went 90 degrees past it. Okay, any questions on that? All right, so some angles that we work with, again, have the same initial and terminal sides, and if they do, that's called a coterminal angle. So all those angles we were talking about earlier, 0, 360, 720, they all have the same initial and terminal sides. So if I give you an angle and I ask you to find an angle that's coterminal to it, all you have to do is add or subtract 360. Yeah, I might say find an angle that's coterminal and positive. So in that case, you might have to add 360. Or I might say find one that's negative. All right, so I'm going to give you a couple examples. And what I want to try to do first is sketch the angle, the best that we can. And then I want to find an angle that's coterminal and positive, and then coterminal and negative. Does everybody have the part above example 1? Okay. So 30-degree angle. So we already know where we're going to put the initial side. But where would the terminal side be for 30 degrees? Just roughly. Maybe just let's start by narrowing it down to a quadrant. Quadrant 1, 2, 3, or 4. Yep, Trevor? Yep, it's in quadrant 1. Should it be about halfway, more than halfway, less than halfway? Yeah, it's a little bit less than halfway. All right, so I'll change the color of that. So there's my initial side. Okay, that'd be about halfway for the terminal. I would say that looks like it's a little less than half. So there's my angle, 30 degrees. Okay, rotating counterclockwise. And now, what would be an angle that's coterminal? And let's start with one that's positive. Go ahead. Yeah, what'd you say, Trevor? Yeah, 390. So 390 is coterminal with 30 and positive. How about an angle that's coterminal and negative? Yeah, negative 330. Yeah, and you can see that very easily if I just go like this. Okay, there's 30. Okay, there's 390, exact same terminal, initial and terminal sides. And there's negative 330, same initial and terminal sides. All right, how about 145? What quadrant would the terminal side be in there? Yep, L. Yep, it would be in quadrant 2. So I'm just going to kind of label these so we can see what we're doing. Now, would it be right in the middle? Should it be closer to 90, closer to 180? Yeah, a little closer to 180. Okay, if you go right in the middle of 90 and 180, it's 135. Just average the two and you would see that that's right in the middle. Okay, so 145 would look, let's see, okay, if that's right in the middle, that's a little bit past the middle. Okay, so there's my angle, right there. All right, so now I want to find an angle that's coterminal and positive. Right, so what's an angle that would be coterminal to 145 and positive? 505, yep. Okay, just add 360 to it. If you want to find one that's negative, just subtract 360, and you get negative 215. Okay, and the last one we'll do like this is negative 45. What's the difference between example C and example A and B, especially when I draw it? What's going to be the difference? Yeah, Tom?
They will rotate clockwise.
This one will rotate clockwise. Okay? The other two I tried to show you that they were going counterclockwise. All right, so this time negative 45. Let's start with our initial side. And the terminal side is negative 45. So splitting quadrant 4 right kind of down the middle. It's kind of like a ray with a slope of negative 1. Yeah. All right, so let's try that color. All right, this time, rotation is that way. If you didn't draw that arrow, I would have no way of knowing which way you rotated to get to it. Okay? Right, and Molly, can you give me an angle that is coterminal and positive? Careful, that would be if you had positive 45.
So,
315. Yep. So 315 is positive. And how about an angle that's coterminal and negative? Rachel?
negative 105.
Yep, that would be negative 405. Okay, so if they ask you to find coterminal angles, that's all you need to do. All right, the next thing we're going to look at is some relationships, either with just a single angle, if it's classifying it by its size, or if we have two angles that add up to a certain value. Okay, so we'll look at some different names here. What's an acute angle? Yeah?
Angle less than 90 degrees.
Okay, that's part of it, yep. It has to be less than 90. Anybody know what else? Yep. It has to be greater than 0. Okay, so if I said to you, is negative 10 an acute angle? The answer is no. It is less than 90, but it's not greater than 0. We don't really classify negative angles as acute or, well, the other word you'll learn in a second. Well, 2 other words. How about a right angle? Molly? That's an angle that is equal to exactly 90 degrees. Does anyone know the next term for an angle that's bigger than 90? Yep. Yep, obtuse. And in that case, how big can it be up to? 180. Okay, so an obtuse angle is an angle between 90 and 180. Okay, so those terms that we just used all apply to just a single angle by itself. This term applies to a pair of angles. Okay, anybody know what it means if 2 angles are complementary? Yeah. They add up to 90 degrees. And they have to be positive. So for example, negative 10 and 100 are not complementary. So another thing you could say here is 2 acute angles that add up to 90 degrees. Because if you said acute, that would automatically mean that they are positive. Okay, and then there's another term. A lot of times we learn it with complementary. You know the other term? Okay.
Supplementary.
Supplementary. And what's that?
When 2 positive angles add up to 180 degrees.
Yes, 2 positive angles add up to 180. Now this time that could happen a couple different ways. You could either have 2 right angles, or you could have an obtuse and an acute angle. Could you have 2 obtuse angles that add up to 180? So an obtuse angle is an angle that's bigger than 90 and smaller than 180. No. 2 obtuse angles could never add up to be supplementary. It would be more than 180. How about 2 acute angles? No. Okay, so for supplementary, you either have an acute and an obtuse or 2 right angles. Okay. Negative angles do not have complements or supplements. All right, so the next thing we'll do is we'll just look at an angle, and I'll just ask you to find the complement and the supplement. Okay, what would be the complement of 48 degrees? Yeah, Rachel? Yeah, it would be 42 degrees. Okay, you just have to have 2 angles that add up to 90, and those do. How about the complement, the supplement to 48 degrees? 132. So that's the complement and supplement. How about negative 18? What's the complement of negative 18? Nothing. There is no complement. Okay, doesn't apply. And the supplement? That doesn't apply either. All right. What's the complement of x degrees? Yeah. So, you lost it. Still thinking? Yep. Go ahead, Rachel. Oh, why not? I mean, Molly?
I was just
Oh, you're just stretching. You're stretching, and I called the wrong person. Allie.
90 minus x.
Yeah, 90 minus x. It's basically, it's like the formula. How do you find the complement? It's 90 minus your angle. And the supplement? Yeah, Allie?
180 minus x.
It's 180 minus x. Okay, so any questions on finding complements and supplements? All right. So the last thing we're going to do is look at what a radian is. Okay? So we're going to kind of try to visualize how big a radian is, and then we'll learn how to convert between degrees and radians. Okay, so radians is just another way to measure an angle. If you take calculus and you work with angles in calculus, it's almost always assumed that the angle is in radians, not degrees. Right, so what I'm going to draw is a central angle. Okay? A central angle is just an angle that's drawn inside a circle, and the vertex is right at the center. Okay, so my angle is made up of rays CA and CB, and those two rays intersect, or they hit the circumference of the circle here and there. And if you draw in that curved segment between A and B, a curve that's part of a circle is called an arc. And this is arc AB. Arcs are not directional. They're not like rays. So you could also call it arc BA, and it means the same thing. Later, probably Wednesday or so, we're going to talk about how do you find the length of an arc. And it all just depends on how big of a circle you have and how big of an angle you have. Okay, so we'll talk about how to find arc length later on. But I'm going to use this diagram to try to show you what a radian would look like. Okay, first thing I want to ask you, does this arc that I drew in red and the length of this radius, which I'll do in green, do they always have to be the same? What do you think? Keep in mind, you can change the size of this angle to anything you want. They would always be the same? All right, let me draw one that looks a little different. Here's my angle, or here's my circle. There's my angle. So here's my arc. And here's my radius. Would they be the same in that one? No. So depending on the size of the angle, this arc length could be the same as the radius, but most of the time it probably wouldn't be. It could be smaller, like the arc in this case is smaller, or if you made the angle bigger, like let's say you made the angle 270, then it would be much bigger than the radius. But if you draw it, and the length of this arc is exactly the same as that radius, okay, which doesn't have to be, but if it is, then you just drew an angle that is 1 radian. Right, so if you took a piece of string and measured arc AB, and then measured the radius, and it was exactly the same, that means this angle right here is 1 radian. Okay, and that fact is going to come back up probably tomorrow or Wednesday when we try to find arc length. This is a special relationship that we can use to start to figure out what is the formula for the length of an arc. Okay, we know that if you have an angle of 1 radian, that automatically means, regardless of the size of the circle, that the arc length and the radius length are the same. And I think it kind of makes sense that a radian would have something to do with a radius. Because even if you just look at the two words, they're spelt very similar. So that still doesn't answer the question at all of how many degrees are in a radian or how do you convert between radians and degrees, but it kind of gives you something geometric you can visualize to imagine a radian. Okay? Any questions on that? Okay, so that's, again, important fact we'll come back to this week. All right, so now how do we convert between radians and degrees? Okay, I'm going to have to give you a fact that at this point I can't prove to you. You're just going to have to trust me that this fact is true, and it's going to help you to convert between radians and degrees. So what I've drawn up here on the board, that's a circle with a radius of 1. And we're going to spend, I think probably tomorrow or Wednesday, we're going to talk a lot about the unit circle. Okay? And all that a unit circle is a circle with radius of 1. Now, in a unit circle, there's some special things that happen when we do trigonometry. So, in a unit circle, okay, and sometimes this is something you might have to read a couple times to get it. But in a unit circle, if you measure the angle in radians, it will come out exactly the same as the length of the arc. All right, so in a unit circle, if you measure the angle in radians, it comes out the exact same number as the length of the arc. Of course, they're different units because you don't measure the length of an arc in radians. An arc length is measured just like you would measure the table length. Feet, inches, centimeters, whatever you use. All right. So let me draw an angle. And I'm just going to make something up. Let's say that that angle was 2.4 radians. Okay, this angle that I just drew. If that angle is 2.4 radians, and let's say this is in inches, then that means this arc would be 2.4 inches. Okay? If this angle was 3.6 radians, that means this arc would be 3.6 inches. Okay, so the size of the angle and the size of the arc are equal in this type of circle. Okay, any questions on that idea? All right, so this is the idea that you need to kind of think about in your head. So we need to find an angle. You can pick anything you want in radians that we already know the arc length for. And that's going to help us to be able to come up with a formula to convert radians to degrees. Okay? What we're going to do here is kind of similar to this. If I said to you, I want to convert between feet and inches. So give me a number of inches that you already know comes out to a nice number of feet. Okay? Anyone give me 12? That's perfect, right? So by using that starting fact, by knowing that there's 12 inches in 1 foot, I can now come up with a formula to convert any number of feet to inches or vice versa. But I had to already know that fact, that in 12 inches there's 1 foot. So there's a fact here that I have to know, and you do know it from geometry. I want you to think of an angle that you can draw in this circle, and you would automatically already know the size of the arc. Anybody think of what you could make this angle? And you would know the size of the arc. Well, let's pick an angle that's kind of common, one that we draw in the circle sometimes. What's an angle that we draw inside a circle a lot? I said we're going to label these angles all the time. 90, sure. All right, so let me take and draw a 90-degree angle. Here's my initial side. Here's my terminal side. And there's my arc. I'll do it in a different color. How much of the circle does that arc take up? A quarter. So we know that if we draw a 90-degree angle, that's a quarter circle. Well, in geometry, we don't work with quarter circles a lot. What do you work with in geometry when you're dealing with circles? You work with the area of a circle sometime, but this isn't about area. The circumference, right? So, if I draw an angle that's big enough that it's the entire circle, then we don't even really have an arc anymore. We have the entire circumference. And there is a way to find the circumference of a circle. We just have to know how big is the angle that takes up the entire circle. Yeah? 360. Here's my initial side. Here's my terminal side. They would be right on top of each other. And here, if I do it in a different color, is my arc. So this is going to be like our, in 1 foot, there's 12 inches. If you have 360 degrees, it takes up the entire circle. Okay, any questions on that? Now, why is that important? Because if we can figure out the length of the arc that takes up the entire circle, that number that you come up with is exactly equal to the angle in radians. So if we can figure out what the circumference of the circle is, that number is the same number in radians of the angle that goes all the way around the circle. All right, so let's see if we can figure out the circumference of a unit circle. Okay, what's the formula for circumference? Yeah?
2 pi r.
C equals 2 pi r. And what would I fill in for r in a unit circle? Yeah, I'd fill in 1. So what's the circumference of a unit circle? And you don't have to give me a decimal. We'll just leave it in terms of pi. It's 2 pi. 2 pi. Now that number, 2 pi, that's the length of the arc. But I told you earlier that the length of the arc is the same as the angle measured in radians. So what would be the size of the angle that goes all the way around the circle? 2 pi. 360 degrees, or 2 pi radians. All right, so now we know that in 1 revolution, or you probably already knew there was 360 degrees, but there's also 2 pi radians. Now, if we divide each side by 2, we can reduce that and make the conversion a little smaller. Pi radians is 180 degrees. And you're going to see pi a lot when we deal with radians. Okay, pi comes up a lot. Now, this conversion is okay, but a lot of times when you give someone a conversion, you don't do it like this. This is like if I was teaching somebody to convert feet to inches, and I said, in 3 feet, there's 36 inches. It's true, and you can use that fact, but there's a simpler way to say it. In 1 foot, there's 12 inches. So when you give someone a conversion, what number do you usually put in the conversion? You usually put 1. Okay? 1 day, 24 hours. 1 mile, 5,280 feet. You usually put 1 in there somewhere. So let's see if we can get a 1 somewhere in this formula. And there's 2 ways to do it. Can somebody tell me how I could get a 1 on one side of that equation? And whatever way we decide to do it now, we're going to do it the other way in a second. And that's going to give us how to convert one way between angles and then convert back the other. Yep. Okay, so let's divide both sides by pi. Okay, divide by pi, divide by pi, and I get 1 radian equals 180 degrees over pi. So if you want to know how many degrees are in a radian, just do that out. 180 divided by 3.14. It's about 50 something. Now, look at this equation. What if I wanted to know how many degrees in 2 radians? What could I do to each side of this equation to figure that out? Trevor? Yeah. Multiply by 2, multiply by 2. Now you have a formula for 2 radians. 2 radians is 180 times 2 divided by pi. What if I wanted to know for 6 radians? Could multiply both sides of this equation by 6. But notice what stays the same every time. Pi over 180. So anytime you want to change from radians to degrees, all you have to do is take your angle and multiply it by 180 and divide by pi. And that's how you change from, well, we did it the other way first, but that's okay. From radians to degrees. Multiply by pi, multiply by 180, divide by pi. Right? Now I said to you there were two ways you could get a 1 in this equation. Let's take what we started with again. Besides dividing each side by pi, what else could I divide each side by? Yeah. I could divide each side by 180. And Molly, what's 180 divided by 180? Yeah, it's just 1. Okay, so that gives me 1 degree on the right, and I get pi over 180 on the left. Now, if you wanted a formula for 5 degrees, I would say just go like this. Multiply each side by 5. 5 degrees is 5 pi over 180 radians. All right, so the trick here, put it back the way it was. If you want to convert from degrees to radians, you multiply by pi and you divide by 180. Okay? Every time. And those two things are very similar. One is pi over 180, one is 180 over pi. So I'm going to show you how you can remember to keep each one straight at some point. But for today, just try to memorize which one is which. The other thing we have to get used to is when you work with radians, they normally don't write RAD. Okay, I just did it at first to show you, but you will never see an angle labeled RAD. If you want an angle in degrees, you do have to put the little circle. But if you're working with an angle in radians, you can just write the number. Okay, kind of like that. That's an angle in radians, 3 pi over 2. If they put the little circle above it, then it's in degrees. All right, so let's try to convert this to radians. So your two choices are either pi over 180 or 180 over pi. Which one am I going to use here to convert to radians? I'm going to use the pi over 180. And here's how you can remember. I'm trying to convert to radians. Okay. If I have degrees in the top and I want it to cancel out, so I'm left with radians, it would have to go in the bottom. Degrees in the bottom, degrees in the top, cancels out. So whatever unit you want to cancel out, put that one in the bottom. Okay, and you're left with 30 pi over 180. And if you can reduce it, please reduce it as much as you can. So what does 30 pi over 180 reduce to?
Pi over 6.
Yep, reduces to pi over 6. And you might have noticed that when I drew a 30-degree angle in this program. Let's go back this way. For certain angles, it doesn't write it as a decimal, and it wrote it as pi over 6. Right? So this program is showing me degrees and radians. Right, let's try 45 degrees. Amanda, what would I multiply by to convert that to radians? Yeah, it's pi over 180. And this time I'll reduce before I multiply across. Taylor, how many times does 45 go into itself? Once? And how about into 180? 4 times. So you're left with 1 times pi divided by 4. So 45 degrees is the same as pi over 4 radians. Actually, any questions on that? Converting degrees to radians? All right, let's try a couple the other way. Now we're going to convert to degrees. If it helps you, if you get kind of stuck at first, pretend that RAD is written here. Okay, I'm not going to write it in future problems, but pretend that it's there. Where would RAD have to go to cancel it out? in the bottom. Okay, and if you look back at our examples, when I wrote RAD earlier, pi was always what had RAD next to it, right there, and 180 is what always had degrees next to it. So anytime you write RAD, pi goes next to RAD, and 180 goes in the top. Or just memorize it, okay, either way. So radians cancels. What else cancels? The pi's cancel too. So now I'm left, well, actually I can reduce 2 goes into itself once. It goes into 180 90 times. So what am I left with? 270. Yeah. So 3 pi over 2 radians is 270 degrees, and you do need to put the circle on it, okay, to tell me its degrees. All right, let's try this one. Okay, Zach, what would I multiply by here to change 2 pi over 3 radians to degrees?
Just 180 over pi.
Yeah. Okay, we want radians to cancel. It's invisible. I didn't draw it. You've got to just know that radians is there. Pi goes and cancels out. And 3 goes into 180 60 times. So what am I left with? 120. Now, notice all the angles I've been working with are multiples of 30 or 45. That's generally when you'll leave it as an exact answer. If they give you an angle that's not a multiple of 30 or 45, they'll probably ask you to round it to 2 places. Okay, so to do a problem like this, literally you just type it in exactly like you see it. So we multiply by pi, divide by 180. That cancels degrees. And use your pi button. Okay, don't use 3.14. It's more accurate to use that. So 500 times pi, divide by 180. It's about 8.73. And again, note, not necessary to put RAD. Right. So you would see this problem just like that. Okay, and that would be the same kind of thing. You'd convert to degrees, but they want you to round it off. Okay, so any questions on that? All right. Okay, so homework tonight will be on 323. Okay, and it kind of skips around a lot because we did lots of little things today, like find the complement, find the supplement, draw the angle, classify it, okay, things like that. So they're pretty short problems. It's 1 through 4, 7, 9, 11, 12, 15, 24 to 26, 30 to 32, then 35 to 37, 41 to 43, 47, and 51 to 53. Okay, so we'll take a look at that tomorrow. And don't forget, my extra help this week will be on Wednesday because the test will be on Thursday.